Hello everyone, you're welcome to this channel once again. Today we have another question from aerodynamic point of view. Now let's read through the question we have today. Consider a rectangular wing with an aspect ratio of 6 with an induced drag factor which equals 0.055 and a zero lift angle of attack of -2 degree at an angle of attack of 3.4 degree. The induced drag coefficient for this wing equals 0.01. Calculate the induced drag coefficient of a similar wing, a rectangular wing with the same airfoil section at the same angle of attack, but with an aspect ratio of 10. Assume the induced factor for the drag and the lift slope, delta and tau, respectively, are equal to each other, that is, zeta equals tau. Also, for the aspect ratio equals 10 and the delta equals 0.105. Now, in order for us to approach this particular question of aerodynamics problem, we have a rectangular wing. The one with the aspect ratio of 6 and another one with the aspect ratio of 10. We were told that the aspect ratio of the first rectangle equals 6, the delta for the smaller wing, which is the one with the aspect ratio of 6, equals 0.055, which also equals to the tau. When we're told the angle of the zero lift equals -2 degree, we were told the real angle of attack equals 3.4 degree, and the coefficient induced drag CDI equals what we're supposed to find, which is 0.01. We have to find the CDI. This is for the 6 wing, this is for the 10. We have to find the CDI for the 10 wing, and the aspect ratio of the second wing equals 10, and the delta for 10, which equals tau for 10, equals 0.0. 105. Now, by using the formula for the CDI one, equals, that is induced drag equation, equals CL2 over pi AR 1 plus zeta, we can deduce that CL squared equals CL squared equals pi AR CDI over 1 plus zeta. That gives us pi times 6 times 0.01 over 1 plus 0.055. Our calculated CR becomes 0.4227. Now don't let us forget that the equation for the slope, that is the CL over the alpha, that is the change of the coefficient of lift to the coefficient to the angle of attack, equals the calculated CL, which is the change, that becomes 0.4227 over 3.4, that is changing angle of attack this time around. And don't let us forget that dCl over the alpha equals A. So dCl, the alpha, which equals A, equals 0.0783 per degree. By converting 0.0783 to radian, that gives us 0.0783 times 180 over pi, which gives us 4.4849 per radian. Now that we have calculated the slope for the first wing, the next thing is to slot in the value of the dCl over the alpha equals A, that equals AO over 1 plus AO over pi AR 1 plus tau, which equals 4.49 in approximation. So therefore, our AO over 1 plus AO over pi AR 1 plus tau equals 4.49. From here we can deduce AO. So AO becomes 5.80 calculated from the equation here. Now that we'll find AO, now let's slot it to the second wing equation. Let us forget that A equals AO again over 1 plus AO over pi AR 1 plus tau again. If we slot in the value of AO into each slot there, and we slot in the value of the second wing aspect ratio, then we have our A. Our A becomes 4.97 per radian, which equals to 0.0 0.87 per degree. Now, by using the equation of the lift coefficient, which is CL, because A into alpha minus alpha of the lift of 0 we can deduce our CL becomes 0.0867 multiplied by 3.4 minus 2. That gives us CL to be 0.47. So our CL becomes 0.47. Now that we have found the coefficient of lift, which is 0.47, then we can slot it into the equation for the induced drag for the second wing of aspect ratio 10. So that gives us CDI 10 equals CL squared over pi AR 1 plus delta. If we slot in all the values, we can find that our CDI for 10 aspect ratio become 0.00772 calculated. So our calculated induced drag coefficient for the similar wing of the aspect ratio 10 equals 0.00772. Thank you for staying tuned.